Guys, so today we will starting from the next chapter after system of particles, the most easiest chapter of your entire 11th syllabus as per me, which is chapter 7, I believe, no, chapter 8, right? Gravitation. It is actually the continuation of the chapter which you have learned in your actually ninth class, right? So many of the things is something just repeatedly taught to you guys. So it will be very easy. That's why I told you one of the easiest chapter in your syllabus in your 11th class, right? So just talking about the introduction as per the chapter gravitation, as you see, is would have learned about no, Aryabhatta, how he said that sun is the center and all the planets are revolving. But before that, Ptolemy said that Earth is the center and the planet is all the planets and sun are revolving around it, right? And after him, around 1,000 years, it is called Copernicus, right? Nicholas Copernicus gave a definite model, right? But he was discredited by the church at that time. But later on, Galileo supported him, right? And Copernicus was even prosecuted for his statement. That is, he said that the sun is the center and all the planets are revolving around it, right? So then, from Denmark, Tycho Brahe, right, made data, right, by his naked and eye analysis itself, and he said that no, it is again Copernicus, what he said is true. The sun is the center and the planets are revolving around it, and Galileo also obviously supported it. And another person who strongly supported what Copernicus said is Kepler, right? And he is one of the famous scientists who based Horse theory. A lot of gravitational laws or gravitational theory was stated, and based upon Kepler, three laws were made by him: Kepler's first law, second law, and third law, right? So let us move on with the Kepler's law. So Kepler's law, right, first law, let us talk about Kepler's first law. As I told before, Kepler's first law, right, it is also called, as you say, that is law of orbits, right? This already present in your textbook as a first point of your chapter, guys. So before drawing, I would like to state the statement. Sorry for drawing. So what does the Kepler's first law state? First law states that the path of a planet is an elliptical orbit around the sun with sun at one of its four sides. That is a planet is revolving around the sun in elliptical path. That is what he said, and the path is elliptical in such a way that the sun is located at any of the foci, right? So your question will be, what do you mean by foci, right? Because you have no idea about what an ellipse is, or what and all are the terms of an ellipse. Now this is something is not present in your textbook, and I am telling you from my side. See, if this is an ellipse, right? So this is called a major axis and this is called a minor axis. This much clear, right? This from here to here is minor axis, from here to here is called major axis. From here to here, this is a half of major axis, hence it is called a semi-major axis. From here to here, it is half of minor axis, hence it is called semi-minor axis. This much clear? And usually semi-minor axis is marked as B and semi-major axis is marked as A. Clear? Right. Now this much clear, I hope. Right. So from this point of view, I'm going to increase the terms which you have to know. Right? Clear? So now you will be asking, what is the importance, or what do you mean by our foci, right? Because in the statement of Kepler's, it is said that the planet is revolving about in the elliptical path such that the sun is located at the foci. So you require to know what is foci, right? So there will be two focus in the case of ellipse, right? So let's say this is focus 1 and this is focus 2. When would I say these 2 points are focus? I will make it sure you understand. Let's say this is the position of planet or any particle which is undergoing an elliptical motion. If P is the position, now let us mark this as two lines, so that PF1 plus PF2 is a distance, right? That is, it is the position of particle P with respect to these points F1 and F2, right? Now let us say another position of the particle P itself, that is P dash. Its distance from F1 and F2 will be what? P dash F1 plus P dash F2. Let's say the particle now has reached this point. Let's say it is A. Then the distance from the points F1 and F2, I can write it as AF1 plus AF2. Can't I write it like this? Yes. That means, see, if these all positions sum is equal, then I would say F1 and F2 are equal. That is, when P F1 plus P F2, right, is constant. Similarly, P dash F1 plus P dash F2, that is with respect to these two foci, right, when a body is moving with respect to these two fixed points in such a way that the sum of the distances from these 2 points, sum of the distances from these 2 points means Pf1 plus Pf2, P dash F1 plus P dash F2, AF1 plus AF2 is always constant, then that path of that particle is said to be ellipse. And these two fixed points F1 and F2 is called focal point. Suppose the particle now reach here, then its position from F1 and F2, I will term it as, suppose this is C, that is CF1 plus CF2, that is always constant. So this distance, that is a particle's position from F1 and F2, is remaining constant, it's not going to change, then that path is a elliptical path. Clear? This much clear? Now I have to elaborate with respect to this elliptical section. You have to know a lot of terms, right? So again I am drawing an ellipse, right? So this is major axis, this is this is minor axis, right? Semi-major axis is A, and this is a semi-major axis A. This is semi-minor axis B, right? Clear? This is also B. I am not marking here. Let's say this is F1, first focal point, and let's say this is F2, right? So as per our Kepler, I am repeating, the particle will be undergoing an elliptical motion, planet will be undergoing an elliptical motion around the sun, where sun is positioned again either at F1 or F2. This much clear? Right. Now know about the terms of ellipse, guys. This is again not there in your textbook, I am taking voluntarily from my side. So this is usually called AE, that is A into, that is the position of any focus or focal point from center of ellipse is AE along the major axis, okay, not along minor axis. Along major axis, F1 is at a distance AE from the center, and F2 will be also at a distance AE from the center, where E is called eccentricity. AE is eccentricity. Clear? Right? Keep that in mind, right? Clear? Now if in mathematics later on you will learn that equation, of just like equation in straight line, there is an equation for ellipse, that is x squared by a squared plus y squared by b squared is equal to 1. This is the equation of ellipse, right? You will learn that in mathematics. In mathematics there is a section where you learn wholly about ellipse, parabola, hyperbola, etc. There you will be learning a lot of equation, right? So there you will be learning that equation of what? Ellipse, which is x squared by a squared plus y squared by b squared is equal to 1, where a is the semi-major axis and b is the semi-minor axis. And there is a relationship between a and b also, that is b squared is equal to a squared 1 minus e squared, where e is what is called eccentricity. These are good to know things, guys. You can just write it down. From this expression you can even take E outside as E is equal to 1 minus B by A whole squared. This is the equation of eccentricity. Clear? Keep this in mind. I hope this much is clear. Right. Now here in this figure I'm going to additionally add some terms. Now distance of this point, let's say this is A and this point is B. From here to here, let us mark it as R1, right? From this point to this point, that is from B to F1, let us mark this point as R2, right? R1 and R2, right? So in maths, in ellipse, right? While let me remove this much section, right? This much equation I hope you have written, right? And I'm going to give another color for R1 and R2 because it looks confusing. This is R1 and this much distance is R2. If R1 and R2 is like this, then in ellipse it is also given that A is equal to R1 plus R2 divided by 2. This and all are the equation which are present in the case of ellipse, guys. You need not by heart this equation, but this much relation is good to know things. Again, I'm repeating, not there in your textbook. Clear? Right. The orbit. So what does the Kepler's second law state? That is very important. Kepler's first law states that the earth or any planet is revolving around the sun in an elliptical path, right? And sun is at any one of the focus of the ellipse. This much clear, right? And I hope you understood the terms in the case of ellipse also. Now moving on to the second law of Kepler's, that is, he said that the radius vector, right, the radius vector drawn from the sun to the planet sweeps out equal areas in equal intervals of time. That is, when a planet, is very easy if you understand with the pictorial thing, right? That is, when a planet is moving in orbit, right, like this, right? So this will be the major axis, minor axis. This is, let us say, one of the focus where I am placing the sun, right? So suppose initially the planet was here, P1, right? Now let's say the position of planet has changed to P2, right? So in one day he is moving from P1 to P2, so that means this much area is swiped from by as per the planet with respect to sun, right? Let's say this area is A1, right? Now later on, after many years or whatsoever, so I'm going to consider that now the position of the planet has reached P3 here, and let's say the position of planet has reached after one day from P3 to P4, right? So when I consider the area it has swiped with respect to the sun, this will be the area, right? Now both of them is the position change of the planet, same planet, and both of them are happening in one day itself, right? Let's say this area is A2. So both is actually area swept by the same planet in the same interval of time, right? So he said that A1 is equal to A2, right? When a planet is moving in an orbit, the radius vector sweep equal area in equal intervals of time, here it is happening in one day, right? This is what is stated by Kepler's second law. So you could understand by pictorial representation better, right? Clear? Now here mathematical thing comes up, right? So that is, this Kepler's second law is in relationship with the angular conservation of angular momentum also. That is, you can derive conservation of angular momentum from Kepler's second law. So sometimes a question will be straight away asked in that form also. Derived Kepler's second law from Kepler's second law from angular momentum, conservation of angular momentum, or derive conservation of angular momentum from Kepler's second law. Either vice versa can be asked. Now what can I say about this section? Let's say here the radius vector is r1, right? And let's say here the radius vector is r2, right? Let us say the particle or the planet here is moving with velocity v1, and here the planet is moving with velocity v2, right? So area, this is just like a triangle. This one is also in a triangle, no? So I can say here the area is the first triangle, can be written as what? This is v1 and this is r1, right? So I can write v1 r1, right? Area is half into b base into height. Half is constant, here also constant, right? So I can write v1 r1 is equal to v2 r2. Half I'm not including, guys, both are half, right? Where r1 is very constant and v1 is velocity, right? So I can write this is base v1 and this is radius r1, right? Take it as a vector concept, guys. So I can write here v is inversely proportional to radius vector. This much is easy, right? Keep that in mind. Now this v1 r1 is equal to v2 r2. This much clear, right? Right. Keep that in mind. Right. Now what happens if I multiply here m1 and here also m1? Because let's say this, or let us write here m2. Right? So this m1 v1 r1 is equal to m2 v2 r2. What do you mean by m1 v1 r1? Or what is equation mvr? Do you know? No? If you don't know, write it down. This, that is L is equal to I omega, you know, right? What is moment of inertia? You can write it as mr squared. This into omega. Place of omega, I can write it as what? V by R. So one term goes off. I can write L is equal to mvr, right? So that is angular momentum. So there is an expression for angular momentum in that way also. If you don't know, write it down, guys. So this is actually L1 and I can write it as L2. L1 is equal to L2 means what? Angular momentum is conserved. In this case, actually M1 and M2 same itself. You are supposed to write M itself. Initially I told you, right? Why? Because you are talking about same particle, right? So initially you are writing V1 R1 is equal to V2 R2. You just have to multiply M in the both the side. So M into V into R is angular momentum initial is equal to angular momentum final. So from Kepler's law, right? From Kepler's law, you derive what is known as angular momentum, right? Now you can go from from here to backside also. That is, you can start with angular momentum. That is, when you consider the planet, suppose its position is from here to here. So initially, let's say for it, the angular moment, the initial angular moment, I can write as m1 v1 r1 is equal to m2 v2 r2, right? Both are same mass. Mass can be removed, so I can write v1 r1 is equal to v2 r2. Now v1 r1 can be written as the area swept, right? So area a1 is equal to area a2. This is what is stated by Kepler. So you can bring Kepler's law from angular momentum conservation law, or you can generate angular momentum conservation from Kepler's law. This is very important. Either statements can be proved with each other. Clear? Right. Now the Kepler's third law comes up. Right? Law of so first one is called law of orbits. So the second law is also called law of areas, and there is another derivation or small statement in the case of Kepler's second law, guys. Again, that is not present in your textbook, but write it down. That the second statement also states that the aerial velocity, right, of a planet, right, a aerial velocity of a planet in its orbit is a constant, right? That is what the second statement of Kepler's law states. That is this is again, so guys, I am not telling you to by heart it, because this section is not there in your NCERT book. That is, he said that the planet, when it is moving in the orbit section, elliptical form, the planets will be having its aerial velocity. It is also having a value. Write it down. Again, repeating, not there in your textbook, is equal to, that is velocity. Suppose this is a particle moving. So here in this section, it will be having v1, or you can say this is v2, and let's say this is v1. That is velocity of the planet. This v1 will be maximum velocity and v2 will be minimum velocity. Then v1 is equal to gm by a into 1 plus e divided by 1 minus e. Similarly, v2 is equal to root of gm by a into 1 plus, it becomes reciprocal now, 1 minus e divided by 1 plus e. Right? Just write down this equation. This and all are neat. Yeah. So as per your textbook, this much portion is there. Only the first statement is there, Kepler's first statement, and second statement is there. Sorry. Right, second statement is there and the first statement is there, and in the second statement, proving of our conservation of angular momentum is also present. There's no problem about it. Okay, right. But the other things which I have talked about our derivation section or detailing about your elliptical section is not there in your textbook, right? Clear? Now moving on to the third law of Kepler's, which is also called law of periods, right? Third law, which is called law of periods. It is stating that the square of time periods of a planet around the sun is proportional to cube of the semi-major axis of its orbit. I hope you didn't understand. That is, suppose right? Suppose this is the elliptical motion of one planet and this is the elliptical motion of another planet, right? So let's say this is two planets position. Let's say this is r1 and this is r2. So this guy is one planet and this is another planet, and this is our sun's position. Of course, this is, I have marked it as foci, right? Clear. So this guy's time period, let's say as t1, and this guy's time period of rotation is t2. So Kepler said that t1, right? Oh, sorry, this one, t1 squared is proportional to r1 cube. Let's say r1 is the semi-major axis. Remember, semi-major axis was marked a, right? This is a of this planet and this is a of this planet, right? Similarly, t2 squared is proportional to r2 cube. This is what our Kepler stated. So the Kepler stated that in the case of an ellipse, right, if a planet is revolving about in this fashion, this is the planet's position now, right? This is a focus. Let us say this is a focus, right, and this is the semi-major axis A, right? So he stated that if this is a planet revolving around the sun is positioned at one of the focus here, then he stated that the time period of rotation of this planet square is proportional to a cube, right? In your textbook, in place of a, it is written as r. That is the only difference. Clear? Right. So these are the three laws which are stated by Kepler. The first law is law of orbit, right? Second law is law of area, and third is called law of periods. Clear? Very important section because in the examination they have asked it as it is. Right. Now suppose the numerical question is asked like this. A satellite is moving in an elliptical orbit around a planet. The maximum and minimum velocities of this orbit are given as 3 into 10 to power 8 meter per second and minimum velocity is 1 into 10 to power 3 meter per second respectively. If the maximum distance of the satellite from the planet, that is maximum distance means this is our, I hope you understood, this will be planet and the satellite will be revolving around it, right? So maximum distance of the planet from the satellite is 4 into 10 to power 8 kilometer. You are asked what will the minimum distance be, right? So it is very easy to understand because nothing has been mentioned regarding nothing has been mentioned regarding time period, right? So you can remove the scenario of third law, right? But velocity and radius has been mentioned, or I can say position has been mentioned, means you can go for law of angular conservation of momentum, angular momentum of conservation, right? So you can write mvr as constant, or I can write same planet, right? So you can write v1 r1 is equal to v2 r2, right? So see, when maximum velocity, then mean radius should be less. When maximum velocity, r2 should be less, right? That vice versa. If you don't know, I will repeat it here. If vr has to be constant, means when v increases, r has to reduce. Similarly, when v decreases, r has to increase. That is the meaning of it, vr constant, right? So I can write again, m is constant. I will write v1 r1 is equal to v2 r2, right? Or I can write r1 is equal to v2 r2 divided by v1, right? So what is here v2 has been written as how much? 1 into 10 to power 3, right? That is the minimum velocity, divided by 3 into 10 to power 8, that is maximum velocity, into r2, that is 4 into 10 to power 4, that is the maximum distance, right? If you don't understand why I am writing maximum minimum, keep this in mind. I have repeatedly telling you guys, when v1 increases, r1 has to reduce. That is the meaning of keeping the product constant. So v1, if it is, I am taking as maximum, right? Then r has to be minimum. Then V2 will be here. Vmax I have written means obviously V2, this will be minimum, then R2 should be maximum. So R minimum is equal to V minimum into R maximum divided by V maximum. Now you can write the values. Minimum value of velocity write down, below by maximum value of velocity into maximum distance of the planet from the satellite. Clear? So you will get the value of around 1.33 into 10 to power 3 kilometer. Very easy calculation. Clear? Great. Now moving on to the next section, which is called Newton's law of gravitation. This is something you have learned in your 9th class. Newton's law of gravitation. Now Newton's realized that if a planet has to revolve around the sun, a force of attraction is directed radially, right? That is, if this is sun, right? This is planet, right? That is, if the planet has to revolve around the sun, then there should be a force of attraction which is acting towards the sun radially, right? And should act on the body. Let's say it should off. If it is not acting in this to and fro motion, then the planet will go off, right? Right, it will be moving in a tangential motion, right? So he also recognized that the forces, again, this type of force which is between the planet and any sun, sorry, not planet and sun, is always proportional to the masses of these interacting bodies and inversely proportional to the square of the distance between them. Right? Because of this statement, he formulated the famous Newton's law of gravitation that states that every body in the universe attracts every other body with a force which is directly proportional to product of their masses and inversely proportional to the square of the distance between them. That is something which you have learned in your low class, not a big deal, guys. So he said that F is equal to G m1 m2 by r square. This is our Newton's law of gravitation. That is a force of attraction. It is usually gravitational force of attraction. It is always attractive. It is never repulsive in nature. It is equal to G into m1 m2 divided by r squared, where m1 is m2 are the masses of the interacting bodies and r is the distance between them, and G is the universal gravitational constant. Right? Clear? This much clear? And G's value, if you don't know, write it down: 6.67 into 10 to power minus 11 Newton meter square kilogram raised to minus 2. And dimensional formula of G, you can take it as m raised to minus 1 L cube T raised to minus 2. That is the dimensional formula of G. Actually, you guys can be, sometimes it is asked to derive the gravitational constants dimensional formula as in your examination also, right? This much clear, right? Clear, right? So so someone asks you whether the force of Earth's gravity decreases with the distance. Yes, it will decrease with distance, because force is inversely proportional to r. When r increases, F decreases, goes on decreasing. Clear? Keep that in mind. Now similarly, we had to talk a little bit about the characteristics of a gravitational force. Right? Someone asks you to write the describe gravitation or the value of G. If you don't know, this value of G was actually found by Cavendish, right? An experiment. I believe you have learned about Cavendish experiment in your lower class. If not, please look into it. Right, so characteristics of gravitational forces. First, it says that law of gravitation of attraction is believed to be valid in the case of bodies in the interstellar vacuum as well as between the bodies in the Earth's atmosphere. Does not depend on the medium between the bodies. That is, always, suppose you are just learning about it between sun and planet, right? The gravitational force even between, you are one of the pen with another pen. So every body in the universe or outside the universe will be experiencing what is known as gravitational force, irrespective of the medium between the bodies, right? That is the first property of gravitational force. Second is the magnitude of the gravitational force is extremely weak for bodies on Earth. right? There's four bodies. Suppose there are two bodies. Suppose there are two bodies, 1 kilogram each, and they are separated by 1 meter, right? Then there will be a force of attraction between them in the magnitude of 6.67 into 10 to power minus 11 Newton, right? This is very small force of attraction, right? You cannot see, it is negligible and unobservable, right? So that's why you don't see two guys when you are walking towards each other, they are not colliding with each other, because their force of attraction is very small and is always attractive in nature. That is a third nature. The gravitational force is always attractive in nature. Now, fourth point about gravitational force is gravitational attraction brings two bodies potential energy at the same time, causing an increase in kinetic energy, right? That is, if it is suppose there are two bodies, right? So there is a force of attraction that is called force, our gravitational force, right? So it will be bringing both of them potential energy, as well as it is causing a change in kinetic energy, so that the gravitational energy is always bringing the total energy as a constant form. That's why gravitational force is a conservative force. Conservative force means actually it doesn't depending upon path, right? Clear? Now, sorry. Similarly, let's move on to the fifth point, that is massive bodies at the distances very much greater than their sizes can be assumed to be point masses. That is, suppose, see, when you consider Earth and planet, they have very huge body, right? So you're actually not, you can just consider them and don't consider them as system of particles, just consider them as a single mass, right? Clear? And they are assumed to be attracting along a straight line, right? Actually the range might be in this section, right? This much range can be there, but we always learn the gravitational force along a straight line, right? Right? And don't exceed, always study the gravitational force existing between the center of mass of the object. Don't go for each particle system, right? Clear? This much is the main points or the characteristics of our gravitational force. Clear? Right. So, so if there someone asks you what is the difference between inertial and Indama principle of superposition, right? Next topic is principle of superposition. That is, if of suppose there is a particle, there is a mass here m, and there are different masses, small masses m1, there is m2, and there is m3, and there is m4, right? And each mass will be experiencing a force of gravitation from small m mass. Let's say this is f1, this is f2, this is f3, and goes on less than, this is f4, and goes on till n particle, right? So as per the given figure, the force exerted by the particle on another particle remains unaffected by the presence of any other particle in the space. That is, by this principle of superposition in the figure given, right? For this figure, I can say that the total force, right? The given force acting on mass, this m, is the vector sum of all the forces exerted by the individual masses in the vicinity. That is, F total will be equal to F1 plus F2 plus F3 and goes on, right? Clear? This is how you write about our gravitational force. This much is something which you can learn from your 9th class syllabus itself. Now this comes, which is the term or the section which I am talking now, is something which you have not learned in your 9th class, right? That is law of gravitation in vector form, right? So I hope you remember what is the force of gravitation, right, between two masses. It is F is equal to g m1 m2 by r square. Let us say this is all, these two masses m1 and m2, right? Clear? And let's say r is the distance between them. So this is force experienced by first pass by with respect to second, and f21 is force experienced by second mass with respect to one. Either way you can understand, right? Or you can say, I'm rubbing it again, guys, because you have to represent it vectorially, right? So let us represent it vectorially. So two axes x and y I have marked, right? Let's say this is m1 and this is m2, right? Sorry, right? So this is r1 position vector and r2 position vector of m2, right? This is displacement vector between r1 and r2, right? That is delta r vector. This much clear, right? Right. Let us say F21, that is a force on 2 due to 1, right? F21 is a force due on 2 or second mass due to first mass, right? And let's say F12 is a force on or force on 1 due to 2, right? Force on 1 due to 2. This is F12 and this is F21. Force on 2 due to 1. This much clear? Right? Right. So I can write F21 and F1 as separate. F21 is equal to G M1 M2 divided by R square, right? Similarly, F21 can be written as what? See guys, here again this is vector form, so you have to give importance to the position also, right? So when I'm writing for F21, you're supposed to write this R2 square from where to where. Oh sorry, with respect to which guy I have to write, it has to be R21, right? R21 square, right, into R21 cap position vector I have to write. Similarly, F12 it is GM1 M2 divided by R12 square and the position vector and the unit vector R12 cap, that gives the direction, right? R12 is from here, sorry, this is R21 vector and this is R12 vector from here to here. This much is very easy, you have learned. This much clear? Now we are going to just change the vector form, guys. Clear? So this term I can write it as gm1 m2 divided by r21 squared. This is r21 vector divided by modulus r21, right? So that this denominator section I can write it as r21 cube, right? R21 cube. Clear? Similarly, this guy also I can write gm1 m2 divided by r12 squared. Unit vector can be written as vector divided by magnitude, right? So this denominator becomes r12 cube, 12 cube, right? Now what is the relationship between r21 and r12? If r21 is in this direction, then r12 is in this direction, so they are opposite, right? So I can write r21 vector is equal to minus r12 vector, right? So here let us say I'm going to replace r12 vector as minus r21 vector, minus r21 vector, right? Clear? I'm just replacing. So this r1 to r21 cube, right? It is magnitude. This is actually magnitude. This is magnitude, right? So magnitude cube, you are multiplying or dividing the same, right? r12 is equal to minus r21, right? In direction, both of them's magnitude is same. Magnitude of r12 is equal to magnitude of r21. The same direction. See, this is r12, this is r21, the same distance, right? So r21 is equal to r12 by magnitude, but the direction is different. That's why we meant by writing minus here, right? Clear? So from this equation, can't I write these two guys are opposite, because one there is minus with the same fraction, right? So I am not going to write f21 as equal to g m1 m2, or I can write here itself now, right? Here I'm going to write here itself, right? Here I'm writing it as what? G m1 m2 divided by, this is magnitude section, so I can write it as r12 cube. I can write r21, replace it with modulus r12 because magnitude, right? Into, it is r21 vector, right? Now compare these two guys now, right? This is same both of them are same, but just an additional minus is there. Hence I can write F12 vector is equal to minus F21 vector. That is, force acting on second mass due to the first mass is equal to negative of force on one due to second mass, or I can say force on first mass due to second mass is equal to minus of force on second mass due to first mass. Clear? That's why when you draw two masses, when force on second mass due to one is in this direction, force on first mass due to the second mass in this direction, right? F21, F12, both are equal but opposite in direction. This is a vector. Let us do some numerical problems, guys, right? Suppose there are two masses, right? There are m1 mass and there is another mass m2. Let's say they are positioned at A and B, right? Then let's say the point C, right? And a mass, let's say m0 is to be placed, right? The question is like that two masses m1 or m2 are kept at a distance r from each other, right? A third m0 has to be placed on the line joining the two masses. It where should be, or what should be the distance of m0 from m1 so that this third mass experiences zero gravitational force? That is the question. Where should I place this m0 between A and B such that the m0 experiences zero force, gravitational force? This much clear? R is the distance between A and B. You can use the last result which you are having for almost all the problems like this. Okay, keep that in mind. So this result is very important for NEET preparation. Let's say this mass m0 is at a distance x from m, right? So let's say this position is C, right? So it is said in the question that the net force at C is equal to 0, right? At point C it is not experiencing any force. That is, the force at C, right, or m0 due to m1 and due to m2 is equal. Right, is if there is a force here pulling in this direction from m1, then the same amount of force is pulled by B, so that the net force will be equal to 0, right? So I can write what is the force between m1 and m0. I can write G m1 m0 divided by x squared. That is the force between these two guys. Now if this entire distance is r and this much distance is x, so I can write this distance as r minus x, right? So now force between m0 and m2, I can write G into m0 into m2 divided by r minus x whole square, right? Clear? Right, so I can cancel G here and m0 here, right? So I can write m1 by x squared is equal to m2 divided by r minus x whole square, right? Or I can write r minus x whole squared divided by x squared is equal to m2 by m1. Or I can write r minus x by x is equal to root of m2 by m1, right? So now you guys can get a value of x. That's why I'm doing this one, right? So r by x minus 1, right, as I'm bringing x both sides, okay, is equal to root of m2 by m1, right? Or r by x is equal to root m2 by m1 plus 1, right? That is equal to, okay, sorry, root m2 plus root m1 divided by m1, right? Or I can write x by r is equal to root m1 divided by root m1 plus root m2, right? Let us bring r to the side, so you will get x is equal to r into m1 divided by m2 plus m1, or m1 plus m2 whatsoever. Or I can write r divided by, bring m1 below, so it will be root of m2 by root m1 plus 1. So you can just by heart this basic equation. Someone asks you the position where a mass should be placed so that it experiences zero gravitational force is r1, or I can say r, not r1 na, r na. Why did I write r here? r divided by root m2 by m1 plus 1. Clear? This is the position of a mass where you will be or that mass will be experiencing zero gravitational force. Clear? Right? We'll keep this in mind. Right? Suppose another question I'm asking. There are two bodies or equal masses are moving along the circle of radius r under the action of their mutual gravitational attraction. Find the speed of each particle. That is what the question. Two bodies are equal mass. Let's say that mass is m, capital M. They are moving in a circle. Let's say that circle is having radius r. Right? So these two masses. Okay. You are asked the mutual gravitational attraction is there. Find the speed of each particle. So for gravitational, so that means if it is moving in this motion means its gravitational force between these two guys are equal to the centripetal force, right? So gm into m by what? Distance between these guys will be 2r, right? So 2r squared will be equal to mv squared by r, right? That will be the circular motion for each particle. That is, the centripetal force which is experienced by this particle should be equal to the gravitational force between these two guys. Then only it can undergo a perfect circular motion. So I can write v squared here is equal to gm by 4r, or I can write v is equal to 1 by 2 root gm by r. Right? So this is a very good equation. Clear? Right. The next question is, I'm reading the question, so while I'm reading, you guys have to write it down. Two identical solid spheres of same mass and material density are placed in contact with each other. Find the relationship between F and R, where F is the gravitational force between them and R is the radius of the spheres. So you're asked what is the relationship between F and R. So suppose there is this sphere, this M, right, and another sphere, let's say its mass is capital M again, and they are at a distance, let's say this is r and this is r. So you are asked what is the relationship between force. F is the gravitational force obviously, and r is the radius of the spheres, right? Both of them are supposed to be same size even if they don't look like same size. Okay, so you can write straight away that F is equal to gm squared by 2r squared, right? That is the distance between the center of mass, right? So gm squared by 4r squared. Now what can I talk about mass? Since they have been mentioning that there is both of them are having same material density, means I have to write the mass in terms of density. So I can write g into mass is equal to volume into density. Now volume is 4 by 3 pi r cube, right? Clear? And into density will be rho, right? And there is a square for it, right? So let us write this density term inside itself. So density square divided by 4r square, right? So you will get 4 by 9 g pi squared rho squared r raised to 4, right? So that means F is proportional to r raised to 4, right? So this is a very important scenario. So there is two spheres of equal masses and radius. If they are in contact with each other, then F is proportional to 4 times the distance between these two. 4 times, not 4 times, 4 raised to power of the distance between these two guys. Clear? Right. Now similarly, let us go for another question. Suppose a body is of mass m. It is split into two parts and the parts are separated by a certain distance. Find the ratio of the masses of the two parts so that they have maximum gravitational force of attraction between them. So very important question, guys. This is again a neat question. Let us say that the mass, I'm just introducing a term, okay? Let's say there is a block here, right? Let's say it is having 2m minus m mass. Just telling a small thing that suppose its mass is 2m minus m. And from there, I am going to remove a mass capital M minus m, right? From 2m minus m, I am removing capital M minus m, means now the mass of this object becomes just m, right? So the after splitting the two masses now is capital M and the other mass is capital M minus M, right? Clear? You can do any way, but this is better for calculation. Now what with this, let's say they are at a distance capital small r between each other. So the force of a gravitational force between them, I can write Gm capital M small m, right, divided by r square, or I can write G by r squared small m capital M minus m squared, right? Clear? Right? Right. Now for F to be maximum, this is very important, right? So it is said that force is maximum. Force will be maximum when the force is not changing with respect to mass. That is, when I can say force is maximum when force is not changing, or I can say df by dm is equal to 0, and or I can say d squared f by dm squared is very less than 0. Keep that in mind. This is the term in the case of mathematics. When would I say a term is maximum? When it is not able to be differentiated further, right? So keep that in mind. So when force is maximum, I can say d by dm. What is force here? G by r squared m capital M minus m squared is equal to 0. Differentiation of this term is equal to 0, right? So differentiating this guy, right, G by r squared is constant, right, and m is constant, then dm by dm is goes off minus 2m, right, that is equal to 0, right? So I can write m minus 2m is equal to 0, because this term is a constant term, this cannot be 0, right? Clear? Right? G by r square can never be 0. So that means m minus 2m must be 0. Right? So that can mean m is equal to small 2m, or I can say small mass m is equal to capital M by 2. So if I write what is capital M minus small m, it will be capital M minus m by 2. That is what? Sorry, capital M by 2. So it is m by 2 itself. So what is ratio by small m by capital M minus small m? It is 1. Right? Clear? Question, guys. Fourth one. Geostationary satellite is orbiting the Earth at a height of 6 r above the surface of Earth. What will be the time period of another satellite at a height 2.5 r from the surface of Earth? Right. See, it is very important you understand the concept. This is again based upon Kepler's second law of that is t square third law, t square proportional to r cube. See, this is the question is like this, right? This is the orbit of a satellite and this is our Earth, right? Let's say this is satellite 1 and this is satellite 2. Right, this satellite is about orbiting on the around from the Earth at a distance 6r, right? So this distance is 6r. So always we measure from the center of Earth, means r is actually the radius of Earth. Okay, so actually the distance of this satellite from Earth is 7r. Right. Similarly, this satellite's distance from the Earth is written as 2.5 r, means it is from here to here, that is 2.5 r. So you have to measure from the center of Earth, means it becomes 3.5 r, right? 2.5 r plus r will be 3.5 r. This much clear? Right. Now you are told that the time period of rotation of this, let's say of this satellite is t1 and this satellite, let us take it as t2, right? So this much is clear. So I know that t squared is proportional to r cube, or I can just write t is proportional to r raised to 3 by 2, right? R raised to 3 by 2, I can write like this, right? So then I can write T1 proportional to R1 raised to 3 by 2, or T1 by T2 is equal to, right? I can remove this proportional and I can write equal to R2 raised to 3 by 2, or I can write whole raised to 3 by 2, or I can write, right, this and all are the ways of writing. T2 is equal to T1 into R2 by R1 raised to 3 by 2. right? Now what is R2? That is 3.5 R. So T1 into 3.5 R. And what is R1? It is how much? 7 R, right? Raised to 3 by 2. Now 3.5's double is 7, right? So I can write it as 1 by 2 raised to 3 by 2, right? And what is T1? As geostationary satellite is told. And what is the time period of a geostationary satellite? If you don't know, it is same as that of the rotation of our Earth, which is 24 hours, right? So T1 is equal to 24. So 24 into 1 by 2 raised to 3 by 2. How would you do it? First do the cube, right? Then you root the root, right? So it will be 24 divided by 2 root 2. So when you cancel out, it will be 12 by root 2, or you can just write it as 12 into root 2 divided by 2. So it will be 6 root 2 as answer. Clear? Mathematical calculation, actually you guys can do it by yourself, right? Now go for the next question. Distance between the sun and earth is R. If the distance is reduced to capital R, right, then the number of days in the year. Now here don't go for R plus R etc. because here relationship it is given, right? You are given that initially the distance of sun and earth is R and now it is reduced to half. That is what has been told. So don't go for the distance between the earth and sun and then do the calculation with respect to center of mass. The straightaway equation you can write T2 is equal to T1 into R2 by R1 raised to 3 by 2, right? Now what is the time period, initial time period of rotation of earth around sun? It is 365 days. In respect to days you are asked, right? Now R2, that is new rate distance between earth and sun, has been reduced to half. Initially it was R, then 3 by 2, right? That is equal to 365 into RR cancels 1 by 2 raised to 3 by 2. I can write it as 2 by root 2, right? Or it is 129 days, right? So it is this option. Clear? Now similarly, let's move on to the next question, sixth one, right? And if the separation between the centers of Earth and the satellite is increased by 4 times the previous value, right? What is the new time period if the initial time period was 5? Very easy. Again, I can go for this initial T2 by T1, or T2 is equal to T1 into R2 by R1 raised to 3 by 2, right? And you are told that the new distance is increased by 4 times, means is 4R and this is R. So RR cancels, so you can just write it as 4 raised to 3 by 2. Right? So what is 4 cube? It is 64, and 64 raised to 1 by 2 is what? 8, right? So T2 is equal to T1 into 8, right? And what is T1 given as 5? So 5 into 8 is 40, so 40 hours. That is answer. Clear? Right? So we are solving the questions very easily, right? Similarly, there are 2 satellites have orbit radii which are differing by the factor 4, means their ratio is 4. So what is their time periods varying? That is your ratio. That is, if you are asked, that is T dash by T is equal to R dash by R raised to 3 by 2, right? So that is equal to, ratio is 4 given, that is 4 raised to 3 by 2. So the answer will be 8. Right? So it is easily solved. Yeah, it is not that tough, right? So the numerical problems are very easy. Yeah. And similarly, guys, this is something again neat section, not there in your problem section. So we have talked about angular momentum conservation, right? In the case of Kepler's second law, m1 m, so both are m1, no? So m1, this is v2 r2. So you cancel these two guys and you write v1 r1 is equal to v2 r2. Right? So in elliptical motion, I have marked R1 and R2. What is R1 and R2? I hope you have the figure with yourself. So R1 and R2, there is a relationship in the case of orbit as R1 by R2 is equal to 1 plus E divided by 1 minus E. Keep this in mind. Because of this, V1 by V2, we can write it as 1 minus E divided by 1 plus E. There is a relationship between velocities of 2 masses, or velocities of an ellipse, right? Or velocity of an orbit which is undergoing an elliptical motion. right? I hope you remember what is v1 and v2. Here section it is v1 and here section the velocity is v2. Clear? Right? And I hope you remember E section, which is eccentricity. Again I'm mentioning it is not there in your textbook. It is mathematical expression, guys. So just mug up those equations, right, and write down the equation of v1 and v2 in your notebook and by heart it. So there is a relationship between v1 and v2, right, and I know that you understand this velocity will be maximum, this velocity will be minimum. So maximum velocity v1 is proportional to, I think I made a small mistake. I'm sorry, I'm extremely sorry. This becomes plus and this becomes minus. Okay, I made a small mistake. It is 1 plus e and 1 minus b, because v1's equation is root of gm by a into 1 plus e, na? Right. So this is 1 plus e and this is 1 minus e. Write down in your notebook. Clear? Again mentioning, not there in your curriculum, only based on your need. So the question as it is has been asked, what is the relationship between, what is the ratio of v1 plus v2? That's why I have writing the expression.